All right, so here we are at topic 39, NLP. And if you take a look at the calendar, tomorrow we're actually going to continue with NLP, even though it's not another topic. Today, this material is pretty much going to cover most things in topic 39, but tomorrow I am planning on going into some of the stuff that's in the appendix that I really do think is relevant and important, and also it's much more cutting edge. Not to say that this stuff isn't powerful or useful at all. They're just different methods, and we'll get into that tomorrow too. Reminder, don't forget your blogs. Also, tomorrow I'll be putting out a poll for which project you would like to work on. I know that we don't get into neural networks until next week, but it's basically image classification. So that will be that option. Okay, so today we're getting into natural language processing. And I want to preface by saying that the modeling aspect of NLP, the modeling aspect is actually pretty much the same as what we've done before. You can take your text data and you can do classification with all the same models that we talked about last phase. You can also do regression with the models that I talked about last phase. You can technically also do a linear regression with text data. What is different about text data is because computers don't understand words, we have to find a way to turn our text into some numerical representation. So today we're going to talk through one group or one subset of ways you can turn your text into numbers. This process of turning text into numbers is known as vectorization. So every data point will be represented by some vector. So any process that goes from text to numbers is called vectorization. So we're going to talk through one vectorization, one main method of vectorization today, and tomorrow we'll talk about another one. Today, just for context, we're talking about bag of words methods. I'll get into what that means later. So the agenda for today, we'll talk about the overall NLP process. We'll actually go through some of the pre-processing steps that you should do for NLP. We'll do some feature engineering as well. And I'll actually show you all how similar this is. Well, these actually also come out of sklearn, scikit-learn. So you can actually kind of incorporate NLP components into like a data science pipeline as well. And I'll show you all how you would go about doing that. And then we're going to do a very, very quick example of NLP classification, doing satire detection. I'm not going to go very in-depth with the modeling aspect because, again, the modeling is exactly the same as what we did last phase. You'll see how that is. But yeah, if there are any questions or anything I can clarify, just feel free to let me know. All right. So to start, text analytics and NLP. So NLP basically allows computers, models to interact with text data in a structured and sensible way. Why NLP is really starting to grow in the last, I would say the last 5 years, I would say, is because prior to that, it was very, very difficult to analyze text data because one way to analyze it is by, looking up dictionary definitions of words and figuring out what they mean. But now that we've kind of broken through that ceiling of figuring out the different ways that we can represent numerically our text data, it's really like, I don't know, like NLP has really taken off since then. So we're going to discuss some steps and approaches to common text data analytic procedures. And in other words, with NLP, computers are basically taught to understand human language, its meaning and sentiments. And this understanding is definitely not the same way we understand language, but it's a way for a computer to kind of numerically get a sense of or numerically represent the text that we're talking about. So some applications of NLP, we have chatbots. Chatbots are actually one of the more recent applications of NLP, especially now when it's not just like, oh, if you see someone use the word no in a message, you give a specific answer. Those are pretty much just like, scan your text, give an answer. It's actually gotten a lot smarter now because chatbots can now infer meaning, very specific meaning. If someone is typing a very specific, I don't know, message situation, that's super interesting. That we'll discuss more about tomorrow. Classifying documents, that's the process that we're going to do today. And also speech recognition and audio processing. We're not really going to deal with audio data during this course at all, just because audio data, usually how people work with audio data is, especially if it's like spoken word, you first feed it through some sort of transcription library, and then you have your text data. So we're not going to work directly with audio files, although there are a couple libraries out there if you're interested that analyze like waveforms of audio clips and things like that, but we don't really, I haven't had much experience with audio data myself. So we'll talk about pre-processing steps, feature engineering, and then other steps that you have to take in order to format text data for machine learning tasks. So here's an overview of the NLP process. Let me zoom in. So we have our raw text over here, and we're going to have rows and rows of raw text. The example that we're going to start with, I think, let me double check. The example that we're going to start with, which I think is the one that we're going to use all the way to the bottom, we're going to go through satire detection. I said that earlier. So we're going to go through satire detection. So we have a bunch of news articles from different sources, some satirical, some not. And we have our raw data over here. We're going to first go through the process of tokenization. That's the first thing that we'll hit. Talk about pre-processing text. Things like is basically data cleaning, but for text. Feature engineering, which is what bag of words comes underneath. Then we'll talk about our model building and model evaluation. Again, exactly the same as what we were doing before. So to start, these are our libraries. The main pre-processing libraries that we'll use, NLTK stands for Natural Language Toolkit. And NLTK has a lot of useful things. For example, these download lines at the very bottom, they're actually downloading corpuses. And corpus basically just means group of text. And so you can see here we're downloading stop words. I'm going to talk about stop words in a little bit. I'm not sure we use punct in this notebook, I forget, but we're also going to use WordNet. And I'll show you all what WordNet is in a little bit as well. From NLTK, we have all of these, which we'll see each one of these in a little bit. But also out of scikit-learn also has text pre-processing libraries. So within feature extraction, there's text, and you'll see these. We actually kind of saw this when we talked about naive Bayes. I'm going to go more into it today. And then these are things that we've seen before. This seems like it's redundant. We have our confusion matrix, our metrics, Seaborn, NumPy. This is super out of order. I don't know why, but these are things that we've seen before. Okay. So the first step of NLP, especially if you're taking these bag of words methods, and I'll talk about what bag of words means later, but first step of doing NLP is tokenization. When you have a long string of text, you should separate them out into tokens. So tokenization is basically the process of splitting documents into units of observations. And we usually represent tokens as n-grams, where n represents the consecutive words occurring in a document. So the most common form of tokenization is just single words. So, you know, when you do like string.split, and it basically separates out based on the spaces where the words are, that is tokenization. However, for NLP, for some purpose, and we'll see why later, you might want to increase that into looking at bigrams or trigrams, where instead of just looking at single words, you will look at pairs of words as well. And we'll have an automated way to do that later as well. So just an example, the sentence David works here can be tokenized into, you know, the 3 single words of David works in here, but also the pairs of words, David works and works here. So doing these like higher order n-grams basically allows us to look at commonly occurring patterns or groups of words basically, and we'll see how that might affect our model later. So as an example, here's a review that we'll work with to start, a very simple review, just a movie review, that's it. So tokenizing, there's actually many different ways to tokenize text, and there are a lot of different libraries that do tokenization. One easier way, and it depends on your definition of easy, is by using Regex Tokenizer. So Regex is something that I'm not going to talk too much about today, but there are a couple labs about Regex in your labs. And I do think if you're very interested in NLP, to take a look at Regex, and there are a lot of online exercises on Regex as well. I'll add some of those resources into the homeroom later today. But what Regex stands for regular expressions. And it's one way that you can kind of filter out or search through text. One very common application of Regex, if you've ever seen you know, one of those forms that you have to like fill in your details, and they ask for like your email or phone number. And sometimes automatically they'll know, okay, this is not a valid email, or this is not a valid phone number. Those are likely using things like Regex. So Regex The language of regex is very, very convoluted in my opinion. This is a regex expression. And it does take some getting used to be honest. For me, I just pretty much Google every regex task I need to do. But regex, you can kind of represent things that you're looking for. So in that email example, what regex can do is, okay, look for like a series of numbers and letters, underscores, whatever other symbols you can do in an email address. Look for an @ sign, look for whatever the domain is, dot, whatever. And so all of those wildcard elements you can actually take into account with regex. So you don't have to be like, okay, I have to look for every Gmail, every Yahoo mail, so on and so forth. And same for phone numbers. You can actually write a regex expression to take into account all different forms of writing a phone number. I know like for phone numbers, some people do like just the dashes in between, like the 334. Sometimes you have like the parentheses in front of the first and then dash between the second two. So those are actually written very likely using regular expressions. But anyways, just to quickly go over what this means briefly, this regex expression, and if you want to define a regex expression, similar to how we do F strings, if you just put an R in front of a string, it becomes a regex expression. And what this means is we're gonna represent to recognize a token is basically any sequence of characters that is from lowercase a to z, uppercase a to z, and can also contain numbers. And this plus basically means like no matter what the length. However, once it reaches a character that isn't one of these, it will stop and then that becomes a token. So that's what regex tokenizer is doing. So if we do this tokenizer, you can see that this starts as one long string. When we do the regex tokenizer, you can see here that it has split everything up. It's also gotten rid of the periods because periods are not included in this expression over here. No commas. Are there any apostrophes in here? I guess not. But if there were apostrophes, it wouldn't be included in this tokenizer. Something to note as well. Let's say there's like a typo and I accidentally put like a bunch of exclamation marks there. That will actually separate them out. So just something that's good to know. All right, let's go back to this. All right, so this is a process of tokenizing. Honestly, if you just do dot split, that is also a method of tokenizing, but then you would then have to strip out the punctuation, so on and so forth. There will be some scenarios that you do want to take punctuation into account. We'll talk more about that tomorrow. Okay, so let's just take a look at our review. So this review has 145 words. And we can look at frequency distribution. So this is like kind of doing a word count. I know we did an exercise back in phase 1, I think, I forget. But we did an exercise where we did word count manually, but frequency distribution is something that exists. It comes out of NLTK probability over here. So just feeding in the frequency distribution, feeding in our tokenized review into frequency distribution, you can see that frequency distribution is not something that we can see. However, we can plot it out. So looking at this graph over here, and let me zoom in some more. Let's take a look at what these words are. The first like 10 or so words, to, he, of, movie, I, a, is, in, it. These words are not particularly important, right? They don't really have any meaning. And these words, a lot of these words are considered stop words, words that will not necessarily help a machine understand what things are talking about. So we want to do something to get rid of these words. Now, for us in our natural language, we need to have these words because this is how we structure sentences, but computers understand language a little bit differently. So therefore, we do want to clean these out because these would just be extra words for the computer to sift through or for your model to sift through. So yeah, are these words very informative? No, they are not. Can we extract useful information based on this frequency distribution of the most common words? I would say at this point, not really, especially if you're looking at the first few, but maybe towards the end, we see like, all right, there's something about the director. There we have movie, but we know this is a movie review. Something about the story, something that they know something beginning, so on and so forth. So let's try and make this a little bit more helpful. So next, there's a process of stop word removal. And from to get stop words, this is actually something that comes with NLTK. So when I downloaded stop words over here, I think you only need to do this once in your once ever on your machine, but if you're doing this in Luminous, you might have to do this a couple times for each notebook. I forget. But basically, this actually stores a series of words in your computer within the libraries package of what stop words are. So to retrieve that, stop words, you can actually get stop words for different languages as well. I have seen one project done in like German before, so that was pretty cool, although I couldn't understand any of it. But I mean, the idea is still the same. As long as you can find a library that knows how to process that kind of text, that's good. So if we take a look at the stop words, these are English stop words, and these are things that are predefined by NLTK to be stop words. So cool, we have these stop words over here. Let's filter our review. So for W and tokenized review, if it is not in stop words, let's just keep that review. So we're basically doing a filter. So after going through the stop word filter, you can see that it's a lot shorter now, but now the words are a lot more relevant or a lot more meaningful. So we take a look at how this has changed. It's gone from 145 words down to 61. This is kind of different from, when you're dropping null values and cleaning up your data frame, you typically don't want to lose too many rows. However, these stop words are not data, it's not really data that you're using. Because these stop words are not semantically useful, it actually makes sense to save on, the redundancy that your model will have to, process all of this text. It's actually better to drop stop words usually. So even though we've gone down to 145 words to 61, that's okay because the core meaning of this text should still be preserved. So let's take a look at the frequency distribution now. Of course, the number here is at 5 versus before is like, I think this is 15. So right now, the most common words are movie, director, trying, say, story, way, make. I mean, this is only one piece of text. Of course, it like kind of ends out at 1 and everything else is going to be one word long. But if you're doing like a large body of text or a lot of rows of text together, this frequency distribution might be more useful. We'll actually see some examples of that later too. Cool. So now with semantically meaningless words removed, this makes a little bit more sense. We have a little bit more context on what this review is actually about, maybe. Cool. So
can you add like custom stop words, like depending on the context?
Absolutely, absolutely. So what we'll actually see later is from this set of stop words, you can definitely add to this list. And then you can just, instead of not in stop words, you can literally add words to this list. If you're doing something that's contextually very specific, you can add your own stop words. Maybe based on your frequency distribution, you're noticing like, okay, this is a movie review. I don't need to see the word movie. You can add that in there. We're going to do that example later as well.
Okay, thanks.
You're welcome. Anything else before I talk about more data cleaning? Okay. So the next thing we're going to look at is lexicon normalization. So lexicon normalization is basically another method to kind of clean up your text such that we're not, basically, again, reducing redundancy as much as possible. So aside from stop words, a different type of noise can arise in NLP. For example, if we look at these words, let me zoom in a little bit more. Collect, collection, collected, and collecting are all very, very similar words. Of course, you can argue in different contexts to be completely different things, but using two methods of stemming and limitization, we can reduce all variations of the same word to the root version of all of its derivations. So for example, I think something that'll be more relevant, maybe collect and collection are different, but collect, collected, collects, those are quite similar words, and we in some cases want our model to treat those as the same word. So if you want to do that, you can use the processes of stemming or limitization. Before I get into stemming, I'll tell you all now that nowadays, no one does stemming anymore. Everyone actually does limitization, but I do want to talk about what stemming is to start. So stemming basically allows us to remove different variations of the same word, right? For example, collect, collection, collecting. Stemming is basically the process of reducing inflection words to their root forms, such as mapping a group of words to the same stem, even if the stem itself is not a valid word in the language. So I believe they use some sort of, I'm not a linguistics person at all, but I think that there is like, there is like a mapping of, every word that exists and what its stem is somewhere, and they actually make use of that to do this stemming process. So for change, changing, changes, changed, and changer, it all becomes changed with no E. That's the process of stemming. So if you want to use stemming, and I think I've already imported this, but whatever. To use stemming, you first have to instantiate the stemmer. And then basically what I'm doing here is I'm appending PS dot, well, PS is the pointer stemmer, dot stem is the method, and I just feed in each word, and we can take a look at the stemmed review. So if we look at stemmed review, it now looks like this. So actually, let me do a print so it's neater. So now it says begin, movie, give, field director, try, portray, some, mean. They've basically cut off the ends of every word. So maybe when you look at the frequency distribution, some noise is reduced. So we take a look at this. We have movie. I mean, this is not a very long review, so there are not many changes. But if you had a lot of like plural forms and singular forms of a word, those would be combined. Cool. So again, no one really uses stemming anymore. So most people actually use Limitization nowadays. And the reason for that is because Limitization returns real words. For example, instead of removing movie with no E like the Porter stemmer does, the actual word movie will be returned by the limitizer. Pros and cons, Limitization actually maps like actual dictionary words. So if collection is a dictionary word, it will not be reduced to collect, which I guess makes sense. And yeah, okay. So Limitization takes all of these, turns them into the actual word change. So very, very similar to that, we're going to use the WordNet limitizer. And the reason why, I mean, WordNet, there are actually a few limitizers. WordNet is the most common one. And in order to use this, if you're running into any errors with using this, you actually do have to download the WordNet package or the WordNet corpus. So quick point over there. Okay, so the process of limitization, very, very similar. So here you can see that we have instantiated the limitizer, and we're going to limitize these words one by one. So movies become movie, collecting, collection, these remain the same as well, and collections gets reduced to collection. And if we compare it with stemming, for movies, stemming turns it to movie with no E, and collecting turns it to collect. I'm actually interested to see if collection also gets, yeah, collection actually gets stemmed into collect, which is interesting. All right, so we can limitize our original review. Right now we can see that our, oh, yes.
Question. So limitizing basically where stemming goes to the root of word, the root word.
Mm-hmm.
Limitizing simply takes out stuff like plurals, but it retains largely retains the actual word itself in its form.
Mm-hmm. That's right.
Okay.
Yes. So typically you'll actually see that the number of unique words that you have out of stemming ends up being less than the number of unique words that you get out of limitization. So pros and cons, if you really want to reduce as much noise as possible and you're okay with some words like collection and collect being treated as the same word, maybe you can do stemming instead of limitization. So it really depends on how you want to treat your data. And when you get a little bit more used to how, and we'll see that, I think it'll become more clear later, but once you see how the models treat each word, you might be able to make that decision based on some context better.
Okay.
Cool. All right. So this is lemitized. You can see that instead of having it look like this, where it's a lot of half words, we now have the full words over here. All right, so those are the main like noise reduction data cleaning steps for NLP, you know, just removing stop words, basically semantically meaningless words, and then also just getting rid of some noise in the sense of like plurals or words that pretty much can mean the same thing. So next we're getting into feature engineering. And feature engineering, there are two main methods of feature engineering in NLP. Bag of words methods, which we're going to talk about today, and word embeddings, which we're going to talk about tomorrow. So right now, the machine learning algorithms that we've encountered so far represent features as variables that can take on different values for each observation. So for example, we can represent an individual with education level, income, so on and so forth. So in NLP, in order to pass text data to machine learning algorithms, we need to represent each text observation numerically. So the process of NLP is really just the process of getting from text to numerical form. One such method is bag of words methods. So bag of words methods, or BOW for short, I actually always say bag of words. I feel like that's fewer syllables than BOW, but it's a way of extracting features from text for use in modeling. Basically, once you go through these bag of words methods, you can pretty much throw the data straight into any of the machine learning models we've talked about so far. So a bag of words is a representation of text that describes the occurrence of words within a document. So it involves two things. One, a vocabulary of the known words, and then a measure of the presence of the known words. And within bag of words methods, there are two main ways to do this. So it's called a bag of words because information about the order or structure of words in the document is discarded. So the order of words, like, what words come before and after other words, it's not taken into account in a bag of words method. The model is only concerned with whether known words occur in the document, not where in the document. So if you think that the order of the words being used matters, then word embeddings, which we'll talk about tomorrow, might be more appropriate. So the intuition behind bag of words is a document is similar to another if you have similar contents. And bag of words data can be represented as a document term matrix or a term document matrix, where each column is a word and each row is a document. And we kind of saw this when we were talking about naive Bayes' last phase. So for example, we have 4 documents over here. I love dogs, I love cats, I love all animals, and then I hate dogs. So this can be represented as, having a column for every unique word. So love, dogs, cats, all animals, and you're basically representing word count. So this is one way that you can do it by just taking the count of words. So you have a bunch of ones for, where all the unique words are, and everything else should be a 0. So let's take a look at how we can do this the scikit-learn way. Or scikit-learn is the only way that we do it. I think I already imported Pandas, so let me clean this up. Okay, so we're going to use count vectorizer, and count vectorizer is basically how you can automatically go from this into something like this. So let's take a look at what this is. First, I have my documents over here, which I've just taken those sentences over there. This can also be like a column in your data frame. That's absolutely fine as well. And then I'm instantiating my count vectorizer, and I'm going to do a fit transform on my docs. And then we'll see, I'll sort of like explain what all of this is doing in a bit too. But basically, this is my data now. I have automatically, it does it in alphabetical order. But yeah, I have my term document matrix right here, just like that. So what's happening over here? Why do I have to do these steps over here? So let's take a look at what X gives us. So if you take a look at X, where we do the fit transform, X is a sparse matrix. And sparse matrix, the reason it is sparse matrix is because in text data is typically very sparse, especially if you're doing a bag of words method. So if you take a look over here, I mean, these are very, very short sentences, but there are a lot of zeros, right? Because not every sentence has every word. And so it's actually a lot more efficient to store sparse data in a sparse matrix. So instead of looking like this, what a sparse matrix is actually doing, it's basically saying, all right, for row 0, and then dogs, we have 1. Row 0, love, we have 1. And they don't even care about everything else. So basically anything else that any other row word pair is not even represented because it knows automatically it's a 0. But anyways, from the sparse matrix, to get to something that we can actually see, we have to add to array. So we do x.toArray. Oops, oh, there's no underscore. To array, we get this. But problem with the array is we lose out on our column names. So our column names are actually stored in the vectorizer itself. So we take a look at the vectorizer. Get feature names is one of the methods out of the vectorizer. That's how you get the names, and these will always correspond to these. So with that, we have our data that we can pretty much give our model. So we're going to do this super quick example at first. So let's just do a very simplistic classification problem. So 1, 2, 3, these are people who love animals. 4, someone who hates animals. So here we're going to represent 0 as animal lovers, 1 as animal haters. So let's set this as our Y. So we're not going to do train test split right now. We'll do that process later on, but just to show you all, if I take the data frame that I have over here as my X values, I can actually fit my naive Bayes model on my data frame and my Y. That works. And I can make my predictions. And I mean, as expected, because there are only 4 data points here, my predictions will be not animal lover, animal lover, not animal lover. So that's how we could quickly, immediately use our data out of the count vectorizer. Before I stop for questions, count vectorizer is actually a step that you can add into your scikit-learn pipeline. So if you're dealing with text data at all and you want to pre-process your text, and I'll show you all actually in count vectorizer, you can do a lot of the text cleaning within the count vectorizer. I'll show you all that later on. But yeah, any questions at this point? Okay. So count vectorizer is one way that you can represent your data in a bag of words format. However, let's just imagine like we're dealing with a set of text that has to do with animals. And a set of text that has to do with animals, let's just say people use the word animal a lot, and those counts are going to be very, very high. But if every row uses the word animal like 10 times, is that going to be useful at all or not? So based on that logic, which I'll get more into in a little bit, based on that, there's another way of vectorizing your data in a bag of words method known as Tfidf. And Tfidf stands for term frequency dash inverse document frequency. So basically what it's doing conceptually, it is weighing the uniqueness of a word. So if a word is particularly unique to a specific text, it will get a higher value. So there's an equation for Tfidf, but we don't have to get into that right now. But just so you know, Tfidf, higher values for Tfidf basically mean that it's more unique to that specific row. All right, so let's just use these examples for now. We have some longer reviews over here. And very similar to count vectorizer. Actually, we'll do a count vectorizer example real quick. Okay, by the way, this is what a sparse matrix looks like, which doesn't make any sense. So this is count vectorizer. And you can see that with a longer reviews, we get more columns. Like immediately, we already have 269 columns. Let's take a look at Tfidf Factorizer. So Tfidf Factorizer, you use it pretty much the same way. You instantiate and then you do your fit transform. Now, this is a little bit less relevant for count vectorizer because count vectorizer, you're not really affected by the distribution of your data. But to be safe, you should always fit transform on your train, transform on your test. Basically the same like any other pre-processing method we talked about last phase. Similar, yeah, so same for Tfidf Factorizer as well. Fit transform on your train, transform on your test. And we'll do that process later on as well. If you look at our Tfidf values, they're all a lot smaller. However, it only matters that they are relative to each other. The values are all relative to each other. So it doesn't matter that they're all like in the hundredths in value. So here you can see that our Tfidf values look like there's still a lot of zeros. And each of these values are basically computed using this, this formula, basically term frequency, which is the word counts, multiplied by the log of the fraction of the number of documents divided by number of documents containing that specific word. So again, about the uniqueness of the word. So if we were to look at an example, what's a good example? If we take a look at, I want to see what word is in everything. I wonder if the word movie is in all of them. Okay, never mind. Okay, so the word movie appears 3 times in review 0 and none in the rest. So we would expect the word movie to have a pretty high Tfidf value. So we take a look over here at movie. Oh, I guess the word movie is not in there. Hold on. Here, like this. Oops, I think I did something wrong. Oh. Okay, never mind. So here we'll look at, all right, never mind. Basically the value for movie should be higher because it is more unique to that. Actually, let's look at it backwards. Apparently there's the word 10 in here. So let's take a look at what that looks like. I think that should be a string. Cool. Never mind then. Oh, I think because I'm overwriting each one. All right, we'll forget about that. by default, the numbers should be higher if it's more unique versus in relation to other rows of your data frame. All right, so now that we have this format, either from Count Vectorizer or Tfidf Vectorizer, we can pretty much already feed it into our model. So we're going to go through a text classification process, but all of the steps that we've talked about up till this point, that's pretty much all you need to know to do a bag of words text classification model, because this is the data frame that you can then plug into your models. In this example, towards the end, we're actually going to fit it to a random forest model, and I'll show you all, like, you can still get feature importances. You can do pretty much all the same modeling steps that we've done before. You do want to see the same metrics, including your confusion matrix, your classification report as well, and the way that you interpret them in context, exactly the same as how you would in the last phase. So cool. Let's deal with our satire problem. So here, what we're looking at a data set that has 1,000 rows. And actually, let's take a look at the data set itself. This is our data set. They are, I think, political satire. So half of these are political satire, half of them are actual political articles. Targets of 1 and 0. You can see that they are also evenly spread out, 500 each. Oh, by the way, you can also do smoked on text data exactly the same way that you would regular non-text data. So df head, df body 0. So this is just an example of text. So cool. Now let's split up our X and Y. And in this case, our X is just the one column of the long strings. And then our Y will be, as usual, our target. So we'll do our data and target first. And first we have to process our data. Now, processing data for NLP can be a little bit annoying because you could go very back and forth with this. And I feel like there are also quite a few libraries that are created to do NLP processes, and they haven't really communicated with each other so much. So there's a little bit of back and forth. So what I'm doing first is I'm actually grabbing my data to first look like a list of lists. And I want to do this to first lemitize my data. So over here, I'm actually doing a dot split. That's just really, really quick tokenization. Dot split for D and data to list. So I actually have a list of lists, a list of lists of all of my articles. So they all look like this. And then what I'm going to do is I'm going to lemitize them first. Is it? No, sorry. This is getting all of our vocabulary. So what I'm doing here is I'm creating an empty set, and I'm updating the set with my lowercase words just to see how many unique words there are. And there are 41,000 unique words. Now, if I lemitize this, I'm basically doing the same thing again, but instead I am outputting my lemitized data. So if we take a look at our lemitized output, and you can just work through this for a loop on your own as well. It's not difficult, but this is our lemitized output. Our lemitized output, noting that let's see if there's anything that looks lemitized. Doesn't really matter, but this is our lemitized output. Now, lemitized output is now still a list of strings, and it has to be a list of strings to go into your vectorizer, unfortunately. So when you tokenize your words to do like your EDA and all that, you kind of have to untokenize before you put it back into your vectorizer. We'll see that in a little bit. So tokenization usually does help with your EDA. You have to put it back together to feed into your vectorizer. We'll see why.
A quick question. I just noticed, so in the first sentence, it did less. And then when we,
Did Dimitri drop? All right. We'll wait like a minute for him to come back. But what was I saying? Okay. Oh, now he's back.
okay.
Hey, Dimitri.
Yeah, I got disconnected.
All good. What were you saying?
Why am I the only one in here?
Oh, no, you're not the only one here.
Oh, it says I am. Okay. Yeah, so it just says it was nothing, ouster of third top, official in la. So it took less and took the two S's out.
Yeah, that's something that is probably an issue with WordNet. Yeah, you have very little. I mean, unless you want to go in and like individually figure out how you want to lemitize each word, Sometimes using built-in libraries, you're prone to these kinds of errors. But let me see if it's like I wonder if it was an issue. Okay, yeah, so it did turn less into LE. Problem of one of the basically the built-in WordNet limitizer. But yeah.
Gotcha, thank you.
You're welcome. All right, so now that we have this lemmatized output, we're gonna take a look at these lemmatized outputs. So we take a look at xlem. Oh my gosh, did I delete that? Okay. So we have our xlem, which I want to put over here. It is I should have printed it out, but basically it's a list of long strings. And this is the format that it needs to be to go into your vectorizer. And you notice that I haven't taken out stop words yet. I'll show you all where I do that later. But first, let's do some overall EDA. So like I think Noel was asking before, you can add words into your stop words list. So things that I'm actually adding punctuation as well. And because some of this data comes from Satire Wire, there are a lot of those like, URLs. So I'm going to get rid of those too. So we take a look at our stop word list. And by the way, you can get a list of punctuation from string.punctuation. So that's really neat. And then if we take a look at our stop word list, or stop word set, I mean, this is our new stop word set. Actually, let me do a print statement so it all comes out in one line. There we go. This is our stop word set now. So you can see it has our the words that we've added ourselves. And we're going to use this later too. So for EDA, because this is classification, still stands. Remember how I talked about the separability of data before when we were talking about classification last phase? Same concepts apply because the problem itself is still classification. So you still want to do a fairly comparative EDA. So for that, let's just separate our data into satire and not satire. And satire is basically anything with a target 1, not satire is target 0. So let's separate those out. Take the body text as well. And we're going to do our quick, basically the same thing that we were doing before. What this is doing is turning it into a list of strings, list of tokens, list of tokens, I believe. And then here we are looking at the unique words in each. So for EDA, we're just going to flatten out those lists and take a look at the frequency distributions, and let's plot them. We're going to plot them out. So we're going to plot them out later. But here you can see that these are our satire most frequent words. Again, we haven't taken out stop words yet. This is for not satire. Cool. You can also look at normalized word frequencies. And the way that you can look at that is you're just doing quick mathematical way. I think you can pretty much also do this using like the value counts if you would like. But normalized frequency, just to see that, okay, the is used pretty evenly across both. Cool, just good to know. And to visualize. All right, so to visualize, what I have here is a bar graph of the two different words. You can add a stop word removal, and I think I do have that somewhere in here. Let's see, if not in stop word list, there we go. We're doing our removal of stop words over here. So apparently the is not a stop word, I don't know, we'll see. But basically, this is very, very simple EDA for a text classification problem. Another very common EDA for text data or anything NLP is word clouds. However, I will say that word clouds are more useful for a presentation, not so much like you don't want that to be your only EDA in your technical notebook, because word clouds, and you'll see what they look like. Word clouds just look like this. It's not very quantitative. Really good for a presentation because it's a very visual way of representing, your word frequencies, but please don't let this be your only visualization that you have. But word clouds are highly customizable as well. The word cloud library, and there are a lot of good word cloud examples that you can find online, but word clouds. Okay, so now to classify, this is our machine learning process. I'm doing my train test split. Of course, here I've made it difficult for myself by just naming it a bunch of different things. I do want to show you all Tfidf Vectorizer's documentation. The count vectorizer documentation is very, very similar to this as well. So within Tfidf Vectorizer, you can see that I am feeding in my stop word set. There's a lot of things that you can do with Tfidf Vectorizer or count vectorizer. For example, you can strip accents if you wanted to, if you have like a lot of random, characters. in your data, you can do that. By default, it will do the lowercase for you as well. This one I've actually never used before, but I've seen a couple people use it if they want to specifically pre-process things a certain way. Tokenizer, typically it's by default is just by word. Stop words. So by default, you can feed it in English and it'll just use the English stop words. But if you want to use your own custom set of stop words, you feed in your set of stop words. Something else that I want to show you all is you can play around with min and max df. So let's say you have a lot of unique words, but you probably let's say you have a bunch of words that only appear maybe no more than like 3 times in all like thousands of your data points. You can actually get rid of those. So you can use min or max df to toggle that, or just use max features that only considers the top however many words that occur across the entire data set. Another one is, where is n-grams? N-grams, oh here, n-gram range. So earlier I talked about the possibility of using like bigrams and trigrams. If you want to consider, pairs of words or like trios of words, you can actually set a range. So 1-1 just means that you're looking at unigrams, so singular words. But if you do n-grams, I highly recommend you do n-grams in conjunction with something like max features, because you can imagine it's going to take every occurring pair of words and make it into a new feature. So your feature set will really blow up if you don't do a combination of max features and n-gram range. And also you will get like a bunch of word pairs that are essentially meaningless, possibly. So play around with a lot of these. These are also things that you can do grid search on. I mean, not many people do grid search on their vectorizers, but if you wanted to play around with, okay, how many max features do I really need? Because the more features that you have, the longer your models will take. So you can definitely play around with that. When I get into office hours, I'll definitely go over this a little bit more in depth. But yeah, play around with the vectorizers, hyperparameters, because there are a lot of them. And I do think it is worth looking into, especially if you're doing an NLP project.
Is there anything that filters out like proper names, or just maybe just like capitals?
Good question. I think it might be vocabulary. Or yeah, you can actually, if you would have to first, I don't think that there is a built-in way to do it. However, there is a dictionary that you can filter words out of. So I don't have that example here, but you know what, I'll put it in Slack later. But there is a corpus that you can download from NLTK, and basically in some of your pre-processing steps, or you can basically use it as like reverse stop words kind of. You can say, all right, if this is not in the English dictionary, we don't look at them. So that's definitely something that you can do. I just don't think you can do that based on this, or maybe you can do it here. I forget. I have to think about it, but I'll put that answer in Slack by the end of the day.
Thank you.
You're welcome. All right, so main thing out of here, we're introducing our stop words in our vectorizer. And then we're going to do our fit transform and our train transform on our test. For Tfidf, it's extremely important that you do this because it is calculating inverse document frequency out of the documents that are in your train set. So cool. Our Tfidf data train, again, it's a sparse matrix. And because you can see that it's a 800 by 21,000. So we actually have 21,000 columns in this data over here. And to look at the sparsity of these matrices, the average number of non-zero elements in vectorized articles. So the average, I guess, article length is 167 words. And the number of columns, percentage of columns that contain 0 is 99%. So it's extremely, extremely sparse data. But anyways, we can instantiate our random forest classifier here. We're fitting it on our trained data, and we can get our predictions out of our trained test. And again, metrics exactly the same as what we talked about last phase. We have our classification report. You can see that, okay, maybe there's slight overfitting. And then we can also have our confusion matrices too. So if you want to use your function that you wrote last phase for this, maybe a little bit of tweaking to account for the words, you can use it as well, because the metrics will be exactly the same, the modeling process exactly the same too. For feature importances, this is a really interesting one. we can look at the feature importances here. Again, for example, here we have like the word Monday is the most important feature. So if you have Monday as a very important feature, it is worthwhile looking into, all right, which class does the word Monday actually appear more in? So I would actually go back to my normalized word frequency and maybe look at where Monday is. And then in terms of normalized frequency, whichever one it turns up in more, I wonder if it's here or not. I guess not. But whichever one it appears in more, that means that, okay, Monday, for example, the normalized frequency is higher in satire versus not satire. Then you would say when you see the word Monday, it is more likely to be a satire article. And these are the words that separate the two classes more. So Monday, even, government, blah, blah, blah. And you, of course, want to do your post-modeling EDA, like I talked about last phase as well. All right, so to conclude, NLP allows us to represent our language in a way that computers can understand. We can use the ML algorithms that we already learned to classify these text documents. You can also run a regression on text. So for example, what I've seen is people have actually done regressions of like stock news and stock price. That's actually very interesting. So if you want to do like some sort of sentiment analysis on the stock, that's been done. However, there are still disadvantages to representing language this way. One of them being the fact that you might lose a lot of meaning when you remove the structure of words. When you're removing the order of words, you do end up losing some meaning, right? And things like, honestly, things like satire might be hard to detect once you remove the structure of words. So tomorrow we'll talk about a couple things. Word embeddings, which is basically other text pre-processing method that isn't bag of words. And also topic modeling. Topic modeling is a clustering method that we'll talk about tomorrow that can basically, based on like a giant group of text, help you figure out what the main topics are being, what the main topics that are being discussed are in your text. So maybe out of these like satire articles, there's a lot of like politics, government, I don't know, elections as an example. So we'll work through that tomorrow as well.
Yeah, I was going to ask, would clustering, maybe just running a clustering thing afterwards, help with getting the meaning back a little bit, since it would?
You absolutely can. You can absolutely run like either k-means or HAC will take very long, but you can definitely run clustering on your text data. And you can run the same clustering algorithms that we talked about last week. Yeah. We talked about last week. So you can absolutely run those algorithms if you would like. The one that I'm going to talk about tomorrow is actually one that's designed more for NLP and actually has a very nice interactive output. And so most people end up using this version. So, and this version is a soft clustering method. If you remember, k-means and AJC are hard clustering methods. So every row will solely belong to one cluster. Now, topic modeling, because, when you talk about something, it could be like a little bit of this topic, a little bit of that. And so topic modeling is a soft clustering method that allows you to see like the probabilities of something belonging to a specific topic.
Gotcha. And yeah, and then I guess you could throw that into something like a recommendation afterwards to try.
Absolutely. Absolutely. So we'll talk about that tomorrow as well.
Thank you.
All right. You're welcome. Any other questions at this point? Going once, going twice. All right, well, if there's nothing else, I will see you all back here tomorrow for more NLP. But yeah, NLP is super interesting. I mean, don't discount the bag of words methods. I think they do seem kind of simplistic, but there have been cases that I've seen bag of words methods outperform methods that, take context into consideration, blah, 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 because sometimes context can be very noisy. But we'll explore those methods tomorrow anyways. All right, well, if there are any other questions, as usual, you can reach out to me at Slack. But if not, I will see y'all back here tomorrow. Bye, everybody.